All right, so in the next section, 3.2, the derivative as a function, we're going to encounter a new way to kind of write the derivative in terms of notation. So just to recap real quick, Newton loved the notation f prime of a. Well, there was another mathematician around the same time that also contributed tons and tons of knowledge to the field of calculus, and that mathematician's name is Gottfried Wilhelm Leibniz. So in Leibniz, liked the notation dy dx, and I think he really liked the notation. I'm not sure. I'm guessing here. But when you think about what a derivative is, it is the change in y over the change in x with some limit as like h approaches 0, or in this case, it's going to be x approaches 0. So change in Latin was delta. So the d is the delta in y over the delta in x, or just change in y over change in x. So to kind of just recap what we did in the previous section, I'm going to use the Leibniz notation, or Leibniz, and we want to find dy dx of the function 1 over x squared. Okay? So the hardest part about this is just taking your time, remembering all the algebra that you've learned up until this point, and applying it to a problem like this that we've never ever seen before. So our derivative, dy dx, is going to equal the limit as h approaches 0 of, now I'm going to go ahead and just use my direct substitution here. So this is going to be 1 over a plus h squared minus 1 over a squared, all divided by h. And to keep things nice and neat, what I'm going to do is just rewrite this as 1 over h times the quantity 1 over a plus h quantity squared minus 1 over a squared. And the reason why I did that is I have fractions in the numerator of the difference quotient. So if I just pull the 1 over h out front, it's still the same exact thing. So let's go ahead now. I'm really going to focus on this part. That 1 over h is just going to come along for the ride. So we have the limit as h approaches 0 of 1 over h. All right, now inside the parentheses, that 1 over the quantity a plus h squared minus 1 over a squared, I'm going to find a common denominator. So to do that, you know what, I'm going to need a little bit more space here, I think. I'm going to multiply 1 over a plus h quantity squared by a squared. So, you know what, let's use brackets. That way, everything looks nice and neat. So here's a squared over a squared times 1 over the quantity a plus h squared minus 1 over a squared. Now I'm going to multiply this by the quantity of a plus h squared over the quantity a plus h squared. So that's going to give me the limit as h approaches 0 of 1 over h. All right, now I'm going to write one denominator. And then I'm going to write one numerator. So a squared times 1 is going to be a squared minus parenthesis, because remember, let me highlight this so you know what I'm talking about. That is going to be one whole quantity there, so you got to make sure you put it in parentheses, okay? So it's going to be minus a plus h quantity squared, because 1 times the quantity a plus h squared is just that. Okay? So now I'm going to simplify the numerator only a little bit. So we get the limit as h approaches 0 of 1 over h. Now my numerator turns out to be a squared minus parenthesis a squared plus 2ah plus h squared all over a squared times the quantity a plus h squared. Remember, the quantity a plus h squared equals a plus h quantity times the quantity of a plus h. So you gotta distribute that. Don't forget about that. I did that in the previous video. All right, so Clean it up a little bit. We got the limit as h approaches 0 of 1 over h times. A squared minus a squared is 0. So you have 2ah negative minus h squared all over our denominator. And as you can see, hopefully, I have the limit as h approaches 0 of 1 over h. And I excuse me, I will show you what I'm talking about. Each term in the numerator has an h, so I can factor that out. So I'm going to factor out the h. Leave me with negative 2a minus h all over a squared times a plus h quantity squared. And by doing that, my h's reduce to leave me with a limit as h approaches 0 of, in the numerator, you have negative 2a minus h all over denominator, a squared times a quantity, a plus h squared. Now I'm going to go ahead and make my substitutions. In other words, I'm going to evaluate the limit. So that's going to give me negative 2 in the numerator, and then a squared times a in my denominator. And that's going to give me negative 2a all over a to the third, which is negative 2 a to the second. Oh, wait a minute. Made a mistake. It's all the way back here. Let me write it in red so you can see it. Sorry about that. That's a squared. I forgot to write my squared. So this is going to be negative 2a all over a to the fourth, which is negative 2 over a to the third. Sorry about the little mistake there. Happens to the best of us. So that is just a recap of what we did in the previous example. And now we're actually using Leibniz notation. Sorry, Leibniz. I say Leibniz. I get lazy. So dy dx equals negative 2 over x cubed. If I wanted to, I can evaluate when x equals a or a equals some value. It doesn't really matter. So now what we're going to do is we're going to kind of change pace here a little bit. Because when we talk about functions, we know that we can go ahead and graph functions. So let me change my paper here real quick because I am not very good at keeping lines straight or anything when I'm writing. So I always just use line graph paper. I think is the easiest. So what I mean by that is this. What we're going to do here is given the graph of f of x, find the derivative. So let me go ahead and let me just graph what we're talking about here, and you're going to see how this works. It's actually really interesting. So now you can see why I need the graph paper. Because it keeps my lines nice and straight, and I like that. So I'm going to go ahead and just plot a couple points here. All right, so here's a graph right here. And this is f of x. What we want to know is, all right, well, what's the derivative? What does the derivative look like? So there's a really easy way to do this. And it all comes down to, do you really understand what's happening at a derivative? So let me kind of exaggerate this a little bit more here. There we go. I like that a little bit more. So if you think about what a derivative is, it is the slope of the tangent line. Now, a tangent line is a line that touches our graph only once. So if I were to ask you, well, come directly underneath here and tell me what this derivative graph looks like, you can use the information from above and figure out exactly how to graph it down below. So up above, like I said, we graphed f of x. Here, underneath, we're going to graph our derivative. And to do that, we use the concept of tangent lines. So there are three very special points on our graph. Right here, and right here. Okay? Now, what makes those points so special is the slope of our tangent line at each one of these points right here is horizontal, which means the derivative has to equal 0. So let me write that down. So at f of negative 3, let me just write this. At x equals negative 3, comma, negative 1, comma, positive 1, our derivative has to equal 0, which means on the graph of the derivative, at x equals negative 3, x equals 1, and x equals positive 1, you are going to cross the x-axis. All right? Now, well, you cross or you touch. We'll figure that out in a second. The idea behind it is our derivative at these points is going to be equal to 0. Now, if you look at the information prior to those points, so let me highlight what I'm talking about. So if we look right here, we can see that all the slopes of our tangent line are positive, which means on the graph of my derivative, I have to be above the x-axis because this is going to be x and this is f prime of x. So they're all going to be positive. And they also get down here, like down here, it's really steep, but the closer you get to that horizontal tangent, the less steep it is. So it means it's like, if you think about velocity, it's like slowing down. So our graph comes down like this, right there. So notice that, and I'm going to circle it. All those tangent lines are positive, but they're all decreasing, and eventually they hit 0. Now, in between negative 3 and 1, so let me highlight that. I'll use a different color here. I'm going to use blue. So in between the interval negative 3 to negative 1, notice that all the slopes of our tangent line are negative. Okay? So for us, that means we're going beneath the graph, or beneath the x-axis, and then we come back up to 0. Okay? Then we come back up to y equal, or the derivative equals 0. Now, in between negative 1 and positive 1, so I'm going to highlight that in yellow, our slopes are positive, which means I'm above the x-axis. So I come up like this. But I know I eventually have to come back down because my derivative at x equals 1 is equal to 0, so I have to come back down. Okay? And then from 1 to infinity, so let me go ahead and let me show you that. So right here, this part of the function, all the slopes of my tangent lines are going to be negative, which means I'm down below here. And what we just did is we took a graph of our function and then we graphed the derivative directly below it. And all you have to do is think about what's happening at the tangent lines. Now, I think, personally, a really good idea is once you figure this out, once you kind of see how this works, create a number line, and right here, you know your derivative equals 0, derivative equals 0, and your derivative equals 0. So at negative 3, negative 1, and 0, your derivatives, or I'm sorry, negative 3, negative 1, and 1, your derivative equals 0. The slope of the tangent line is a horizontal line. That's 0. And then in this interval, so we'll call it interval A, which is going to be negative infinity to negative 3, all of your slopes are positive. So you just put a bunch of plus signs. Then in between negative 3 and 1, all of your slopes are negative. So just put a bunch of minus signs. Between -1 and 1, called interval C, everything's positive. And then from 1 to infinity, so 1 to positive infinity, all your slopes of the tangent line are going to be negative. So you just put a bunch of minus signs. And as you can see, this goes up, down, up, and then back down, which is exactly what f of x equals. And then down below on your graph of your derivative, above, below, above, and below, meaning, and I'm going to go ahead and just circle it as I go. So above, then below, above, and below. And that's how we go ahead and we graph our derivative, is we use the information from our function. And you could do this in reverse. So let me show you an example of doing something like this, in reverse. So now let me use a different marker. So given the graph f prime of x, find f of x. So what I'm doing here is I'm giving you the graph of the derivative. What I want you to do is go ahead and find what the actual function looked like prior. So here, this is x and our derivative. All right, so there we go. Just a simple little parabola, okay? Now, if you think about this, let's just draw right underneath x and f of x. Here's what we know. We know f prime of 2, or I'm sorry, f prime of -2, derivative equals 0. F prime of positive 2, my derivative equals 0. So if I come underneath here, I know that at -2, I got a horizontal tangent. So at f of -2, horizontal tangent, f positive 2, horizontal tangent as well. The question becomes, where is it? Well, look at all the slopes of your tangent lines right there. All right? Remember, this is your derivative graph. They're all positive, which means on f of x, I got to be coming up, because all of these have to be positive. Your derivative graph says they're above the x-axis, so they're positive. Also, it reaches 0 at -2. So I know I need to have something that looks like that. Okay? Because I have that horizontal tangent right here. There's my horizontal tangent. Okay? Now, in between -2 and 2, let me highlight. In between -2 and 2, the derivative is negative, which means in between -2 and 2 on my function, all my slopes are going to be negative. So they're going to be coming down. And I just kind of just lightly draw it like going down. Okay? But eventually, they start to go back up. So I have to have negative tangents, but then it has to start coming back up somewhere. Okay, it has to just turn the corner somewhere, because I know I have another horizontal tangent at f of 2. So, since they're all negative, we're going to have it negative, but then we're just going to come right back up. So right here, there's that horizontal tangent again. And from 2 to infinity on my derivative graph, let me use a different highlighter here. So after my tangent line, or after my horizontal tangent, I need to be more specific, I'm positive, which means this is going to level off and then come all the way back up as such. So given the graph f prime of x, find its find the original function graph, it's right there. It's just gonna, it actually looks cubic because it goes, from left to right, it increases, decreases, then it increases again. So that's as hard as that gets. It's just a matter of understanding what the derivative tells us. In the next section, we're going to go over a bunch of derivative rules, and that really helps out the algebra. It makes things a lot easier. You're going to love derivatives after section 3. So I will see you in the next video.